So in the following lecture, what we will see is a technique that is not so much used nowadays because normally we don't have these problems, but it is useful to know that it exists just in case that you have a protein for which you cannot successfully construct an initial volume. So this is an experimental technique called random conical tilt. The idea is that you take two images tilted by 60 degrees or 40-50 degrees, and you take two micrographs, one at 0 degrees and another one at 50-60 degrees. And the first thing that you need to do is to find the correspondences between points, and then you must identify that, for instance, these four particles here are these four particles, and then you click the pair. So you say this one is this one, this one is this one, this one is this one. This is a very tedious process, especially because sometimes there can be big jumps and there are no distinctive features that allows you to make the correspondences, like the example up here. And there is an algorithm implemented. This is implemented in XMIP, and it is available through Scipion, that allows you to automatically pick your particles in one of the micrographs, automatically pick in the other micrograph, and then find the correspondences automatically. And this technique is very useful. And then here you have some results of how it works, and it works by constructing triangles and finding correspondences between these triangles. And then this random conical tilt, by knowing what is the relative angle between the two micrographs, it allows to automatically reconstruct a volume, an initial volume. It has a problem, that is, it has a missing wedge, and this missing wedge can be alleviated or completely removed if, instead of taking an image at 0 and then 50 degrees, you take an image at 45 degrees and then another image at minus 45 degrees. And then between these two images, the angle is 90 degrees, and then you can automatically determine the initial volume without any missing cone. And there is in the original formulation, this the mathematics behind the correspondences can be rather complicated. You have the whole description in that paper. But there is a very simple intuition, that is, when you tilt, there is a compression of the information along one of the axes. So in the original derivation, this axis was supposed to be vertical. So all the complication here is due to the fact that the axis doesn't need to be vertical; it can be arbitrary. But the idea is that by finding these correspondences and knowing this angle, this tilt angle between the two data sets, then you can successfully reconstruct. And again, the details can be rather cumbersome. But so what that paper brought in was we extended the theory for arbitrary tilt axes, and we align the tilted images with respect to the classes, not with respect to the untilted images. And this brought another advantage, because the classes, so the classes is the 2D average classes. These classes have much better signal to noise ratio, and they can allow a much more faithful angular in-plane alignment. And we explicitly considered mirrors, and because in the 2D class, there can be images that are mirrored or not, and we explicitly considered picking errors. Again, details we can skip. There is this problem of the missing cone. The reason is related to the central slice theorem. So every projection that we have from an object gives us a plane in the 3D Fourier space. And so let's say that we have this object, we have these projections, and these projections are filled into the 3D space. So more or less they sample the 3D space in a more or less regular way, except for a cone. So in this cone there is no information, and the effect of that missing cone is that there is an elongation along the direction of the missing cone. So the reconstructed volume will be longer along that direction. But aside from that, if you have correctly oriented these images, apart from the 3D elongation, the reconstruction is pretty good. And here you have an example of a random conical tilt with only 13 pairs, 13 tilt pairs, so only 13 images of this 13 of these pairs. So this one goes with this one goes with this one, only 13 images, and we will see the quality of the reconstruction. So if you use 32,000 images in this particular example, we got this 3D reconstruction. When we used the old RCT implementation that didn't have all these improvements in the theory, this was the 3D reconstruction, and this is the one with the revised random conical tilt. So you see the details here with only 13 images. So this is an extremely low number of images to have an initial volume, but you can see that the important details of the structure, they are successfully captured by this initial volume. So in practice now, there are so many algorithms for the initial volume problem that typically you don't need any one of these experimental techniques. But just to know, just in case that you cannot successfully construct those initial volumes, it is really good to know that this technique exists. And here you have the same structure. So this is using all the 32,000 images, and this is using 13 with the revised random conical tilt implementation, and this is with the old one. And that would be all.